Global AI development has triggered an energy consumption curve that legacy power infrastructure cannot physically support. Data centers demand massive, continuous streams of electricity. Meeting this 24/7 industrial draw is mathematically impossible to achieve purely by stringing new transmission lines or expanding intermittent wind and solar farms. The metric that dictates true grid reliability is capacity factor, the percentage of time a power source is actually generating electricity at maximum output throughout the year. Looking at this breakdown of capacity factors across the U.S. energy grid, nuclear power dominates. It operates at over 92% capacity, meaning it produces uninterrupted baseload power at more than double the reliability of wind or solar. To sustain domestic heavy industry and the exponential growth of artificial intelligence, the United States has to scale high-density nuclear baseload. In May 2025, 4 executive orders established a plan to modernize nuclear regulation, unblock supply chains, and reinvigorate the industrial base. This initiated a rigid, dual-track deployment strategy. The objective is to separate near-term logistical hurdles from long-term physics challenges, creating a bridge across the commercialization gap for advanced nuclear technology. Track 1 focuses exclusively on advanced fission. Between 2025 and 2030, the government is treating this strictly as a logistics and supply chain problem. Track 2 extends through the 2030s and beyond. This commercial fusion track focuses on solving extreme engineering bottlenecks. By dividing the labor into these tracks, the strategy isolates the immediate industrial scaling of fission from the foundational science required to eventually capture fusion. Track 1 prioritizes speed. The fastest way to inject massive carbon-free power is to resurrect heavy infrastructure that was already built but taken offline. The Department of Energy authorized a $1 billion loan to restart Unit 1 of 3 Mile Island, specifically to provide a dedicated 835-megawatt power stream for tech companies. Concurrently, a $1.52 billion loan was issued to recommission the dormant Palisades nuclear plant, returning an additional 800 megawatts of reliable power to the Michigan grid. These rapid, high-profile restarts are a direct reaction to the market demand for zero-carbon baseload power from operators of hyperscale data centers. But resurrecting dormant facilities only plugs the immediate gap. The strategy is hard-capped by the finite number of viable legacy sites available to restart. To scale beyond existing gigawatt plants, the architecture of fission has to become decentralized. The Genesis mission targets this decentralization by opening up federal land assets, including Idaho National Laboratory, as deployment zones for local data center hubs powered directly by localized reactors. These are Generation 3+ small modular reactors, or SMRs. They operate as factory-manufactured modules, outputting between 50 and 350 megawatts. The extreme endpoint of this decentralized model is Project Pele. Built by BWX Technologies, this high-temperature gas microreactor outputs just 1 to 5 megawatts. The Pele microreactor is entirely transportable. It is ruggedized and designed to be shipped in standard 20-foot shipping containers directly to the point of need. While miniaturizing reactors eliminates geographic constraints and long-distance transmission loss, it introduces a severe logistical bottleneck: the continuous distribution of highly specialized nuclear fuel to thousands of decentralized locations. Advanced microreactors and SMRs do not run on standard uranium fuel rods. They require high-assay low-enriched uranium, or HALEU, often packaged into specialized TRISO fuel particles. Historically, the United States relied heavily on foreign supply chains to enrich HALEU. Sourcing fuel for decentralized domestic power from overseas introduces an unacceptable vulnerability to the national grid. This flowchart maps the federal response: a $2.7 billion investment and a Defense Production Act consortium designed to forcefully stand up a domestic enrichment pipeline, converting raw materials into distinct LEU and HALEU fuel lines. Scaling advanced fission does not require new physics. It requires the raw industrial muscle to construct and maintain a deeply complex, specialized fuel supply chain. Commercial fusion, the focus of Track 2, requires an entirely different industrial approach. Private capital has poured over $8 billion into fusion startups, with the goal of achieving net energy gain plasma events by the late 2020s. This timeline acceleration is driven by high-temperature superconducting magnets, allowing private startups to shrink the size of fusion devices and drastically lower capital costs. But reaching net energy in a controlled laboratory setting does not yield a functioning, grid-connected power plant. Private fusion companies are successfully confining violently lowing plasma cores, but they are not yet equipped to engineer the massive balance of plant systems required to extract that heat and convert it into electricity. If physical infrastructure is not developed in tandem with the plasma physics, these private startups will hit a severe commercialization wall in the early 2030s. To prevent this stall, the Department of Energy launched a Build, Innovate, Grow roadmap to backfill physical infrastructure gaps that private companies cannot afford to solve alone. This timeline shows the public-private division of labor. As private startups race to deploy commercial pilot plants, the public sector is building testing facilities to support them. The public roadmap segments into 8 infrastructure streams, focusing on fuel cycle development, blanket testing, and high heat flux management. This includes constructing fusion prototypical neutron sources. These are testing platforms required to prove whether structural alloys can physically survive the continuous neutron bombardment of a fusion reaction without degrading. It also involves building massive integration facilities to handle the complex tritium fuel breeding cycle and the highly radioactive remote maintenance systems. By funding the foundational material science and testing environments, the U.S. government is acting as the ultimate risk absorber, taking on the heaviest engineering costs to ensure commercial fusion reaches the grid. Executing this massive hardware deployment across both tracks requires dismantling decades of Cold War-era bureaucracy. The ADVANCE Act of 2024 structurally altered how the Nuclear Regulatory Commission evaluates and licenses next-generation reactor technologies. This diagram maps the crucial policy shift, the explicit separation of fusion regulation from the legacy framework that governs fission. Fusion technologies now follow a bespoke, streamlined path. Erasing regulatory ambiguity is just as critical as achieving net energy gains. Without a clear path to licensing, institutional capital will not fund the construction of commercial pilot plants. The U.S. nuclear sector is moving from a posture of basic laboratory research toward industrial deployment. The relentless 24/7 power requirements of heavy industry and AI data centers have forced this transition. Track 1 answers the immediate call by reactivating gigawatt facilities, deploying SMRs, and forcefully domesticating the specialized fuel supply chain for fission. Track 2 secures the long-term baseline, synchronizing private magnetic confinement breakthroughs with a rigid public roadmap to solve the extreme materials engineering of fusion. Mastering the grueling physical logistics of fuel supply chains and the engineering of reactor materials is now the final hurdle for energy dominance.